Welcome back, folks, to Scripting for Linguists. In this episode, let's look at this question. How can we semantically organize concordances, also known as keyword and context lines, in a corpus? If you know anything about corpus linguistics, you're likely familiar with this idea, the concordance line, where you have a word in context, the left and right context of a node word. That's the most basic way of using a corpus is to look at words and phrases in context. The reason I bring this up now is because I just got home from a conference. I got home from the Corpus Linguistics conference held in Birmingham, England, in late June and early July of 2025. And I went to a pre-conference workshop given by Stephanie Everett and her colleagues/students, I believe, Nathan and Sasha, about reading concordances with algorithms. And they use a particular interface here they've created this particular interface here to do that. They have a good number of algorithms that can be used to try and read concordances and do different things with concordances. The one that I want to look at here that they showed in the workshop is using sentence embeddings to semantically organize concordance lines. And they're using this all mini LM L6 V2 model. Now, the purpose of this video is to not go through this interface. I just bring it up because I need to give credit where credit is due. And they use this model here that's available in Hugging Face, this all mini LM L6 V2 model, which is a sentence transformers model. It maps sentences and paragraphs to a 384-dimensional dense vector space and can be used for tasks like clustering or semantic search. And it's a popular model, at least right now, with 91 million downloads last month at the time of recording this video. And so I want to take this model and see if I can do k-means clustering to semantically organize concordance lines. So what we're going to do is we're going to look at two corpora here. First thing we're going to do is we're going to pip install the sentence transformers, just following their and the documentation for this model, right? Pip install. Here's their toy example right there. And they have two sentences. This is an example sentence, no punctuation. Each sentence is converted, no punctuation. Okay, so we'll use that. And I'm going to use two corpora in this video. One is Saints, which is a history of the Church of Jesus Christ of Latter-day Saints, a 4-volume history. And I scraped those chapters, each of those chapters from the church's website, and save them to JSON files. I'm also going to use Brown, the Brown corpus, the OG corpus of modern corpus linguistics from Brown University from 1961. There are 500 texts in text files. We'll use those two. Okay, so the first thing we're going to do is just install some or load some modules that we'll need. Here are some helper functions. We don't look at these in too much detail. This one perhaps let's look at in detail. This get context helper function I defined gets the surrounding context of a node word. And so, one of the most basic techniques in corpus linguistics is this concordance line. And you have left and right context, and you can specify how much context you want. You want 10 words or 20 words or 50 words on left and right of the node word. That is the word you search for. And so I define this function to do that. I currently have it set to 10 words on either side of the node word, but you could set this to 5 or 7 or, like I said, 25 or whatever. I have it set to 10, but again, you can specify something else. And in fact, I haven't yet done an exhaustive analysis of what's the optimal number of words on either side of the node word to give to the large language model to get the best performance with the clustering algorithm. But for now, we'll just set it to 10. Good. So the first step is to get all the words in each of the files into a dictionary. That's what I'm going to do here. You don't have to do this. You could just loop over the text as you're going through and getting the concordance lines. But I'm going to put them into a Python dictionary where the key is the file name and the value is a list of the tokenized words. So there's the file names there, and then here's where the actual putting them into a dictionary happens. Okay, So we don't need to get too in the weeds on that. And then we're going to look at banks. So a classic example of words that have different meanings, or a word that has different meanings, is bank or banks, right? A bank can be the side of a river, right? Or it can be a financial institution where you make deposits, you take out loans, etc. So we'll look at banks, and I'm going to create pandas data frame to hold the concordance lines to make a concordance lines display. And good. So apparently there are 68 occurrences of bank or banks in Saints. And if we look at those, here they are, just in a Google Colab view. Joseph took him by the hand, helped him onto the bank, and embraced him. The baptisms, some men stood along the bank a short distance back and heckled the believers. Banks of the Missouri River. Okay, office buildings and banks where wealthy men transacted business. Okay, that third one is a financial institution, whereas the previous three were bank of a river. This one, the fifth one down, banks of the fishing river, opposite bank over camp. Okay, that's another river bank. Here, this sixth one down, or seventh one down with the index of 6, is an institution, a financial institution again. A village bank designed to boost Kirtland's struggling economy. So the point is we have both banks of a river as well as money banks together. Okay. So what we can do is, I didn't show you, but as I was creating that concordance display, I also kept track of the sentences. I created a little empty list called sentences and just appended each of these left and right contexts with the node in the middle to that list. Those will be our sentences that will throw at the sentence embedding model and have it create a multidimensional space, 384 dimensions, right? Now, the numbers that come out of that, let's just actually take a look here. We'll just run this. I already did. But so we have this data structure, which has 68 rows and 300 and, well, these aren't rows. This is a big list. We can just take a look at it, actually. Let's just print out the embeddings. And we should see a bunch of numbers. Yeah. So each of these lists here has 384 numbers that are the embedding numbers, the vector numbers of the first sentence. The first, again, I'm going to air quote sentence. It may not be an actual sentence. It probably isn't. If I go 10 words to the left of the node, 10 words to the right of the node, I may or may not actually have a full sentence. It could be within one sentence, or it could take in some other words from the other surrounding sentences. But anyway, there are 384 numbers, floating point numbers, that is numbers with a decimal component, that are the vector for this sentence. And so we have 68 of those sets of 384 numbers. That's what it looks like. So then we can take those numbers and do k-means clustering. Good old-fashioned k-means clustering. Now let's stop for a second and talk about that. K-means clustering is, as w3schools.com says, k-means clustering is an unsupervised learning method for clustering data points. The algorithm iteratively divides data points into k clusters by minimizing the variance in each cluster. Okay, so the idea is it's an unsupervised, meaning there's no human input. You just give it a bunch of numbers and it says, how many clusters do you want? And you say, I want 2, or I want 4, or 5, or whatever. And it puts them into n number of clusters. So we're going to take our numbers that we just saw a second ago, all of these numbers, throw it at k-means clustering, and then look at the results. Now I'm going to skip this point and skip this little block for the moment. We'll look at this in a minute. Well, actually, that's fine. Let's just do it right now. So this right here, they talk about in this this tutorial. This particular tutorial talks about how to estimate the best value for k, like how many clusters should I specify for this data. And they talk about using the elbow method. The elbow method to try and find the best number of clusters, or k, to specify. And it looks like an elbow because when you, say, for example, go from 1 cluster over to, say, 10 clusters, and then you plot up the inertia metric, which is a type of metric, you can see that right here at 2 clusters in this particular search, there's a little bit of an elbow, meaning it goes from here and there's like a little elbow. I think that's why it's called an elbow method, because it kind of looks like a joint, right? Forearm and the lower arm. So this is saying that 2 clusters would be good to look at. Well, that's probably a good number of clusters to specify for this particular search. So if we come down here and say, yeah, give me 2 clusters, which I say right there, and that gets used right there in the k-means cluster coming from the scikit-learn module in Python. And here are the actual labels. These numbers are just labels. So this number 1 is cluster number 1, and 0 is cluster 0, the ID of 0. I also have to print out the number of occurrences or concordance lines in each of those groups. So there are 50 concordance lines that were assigned to group 0 and 18 assigned to group 1. That's what that is. And then I add those labels to my concordances, and then I just display them. So here we have the same thing as we saw above, but now we have a new column here on the far right. On the far right, we have cluster. And we have 1, 1, 1, 0. Let me remove myself for a second if I do that. Yeah, we have 1, 1, 1, 0, 1, 0. So those are identifiers. They're just IDs for the cluster that this concordance line was assigned to by the k-means algorithm. And so that's cool. It might be better to actually look at these in turn. So let's look at cluster number 1 only for a second. Okay, let's take a look here. Here we have Joseph took him by the hand, helped him onto the bank, and embraced him. That's a river bank. Baptism, some men stood by the bank, a short distance back. That's a river bank. Banks of the Missouri River. Yep. Banks of the fishing river. Yep. Opposite bank, they camped. Yeah, that's a fishing. That's a river bank. Banks of the River Ribble. Along the bank of the river for 10 miles. Yep. Banks of the Shoal Creek. Banks of the Mississippi River. Mississippi River. Yeah, stranger climb up the bank. So these, just a hand check I've done here real quickly, these are all river banks in group 1, cluster 1, or cluster 0. The ID is 0. Let's go look at the cluster with an ID of 1, and let's make it look a little bit better this way. Okay. Okay. Oh, wait, I think I need to, sorry, let's go back. Oh, yeah, I reran it. Okay, here's the point I need to point out. When you rerun it, it may get new IDs. So before I started the video, I ran it, and cluster 0 was riverbanks, but now cluster 0 is financial institutions. So it says office buildings and banks where wealthy men transacted business. The opposite bank, that one is actually a riverbank. Kirtland Safety Society, a village bank designed to boost Kirtland's struggling economy. That's a financial thing. Other small banks in the United States, yep. Loans back with interest, the bank would turn a profit, yep. Money bank. Hard money, the bank would sell shares of stock. Okay, that's all financial. So by and large, cluster 0 in this particular run are money banks, that is financial institutions. Although we have an exception here. That second one there is a riverbank. So you'll see that's not perfect. But by and large, we're looking at financial institutions. Banks in England and the United States, economic collapse, banks calling in debts, yeah. And then if we look at a cluster with an ID of 1 and look at some concordance lines here, these again are the riverbanks, by and large riverbanks. In fact, I wonder if I can just skim and find an exception to this one. By and large riverbanks, I think those are all riverbanks. Cool. So that worked fairly well. There's one exception with the financial institution banks where it was a riverbank, but right, should have been a money bank. But that's kind of cool. To take these numbers that come out of the embedding model, these vectors of numbers, and use k-means clustering, a simple algorithm that runs very quickly. So let's try this again. Let's go back up and recreate some stuff here. Let's look at Brown corpus now. Brown corpus, the OG of the corpus linguistics world. 500 files, yeah, that's right. There are 500 files in Brown. And we're going to populate a dictionary to hold the text Should be pretty quick because I'm doing a manual tokenization here. It's just a brute force, naive regex, regular expression based tokenization. I'm fully aware, and I tried some more sophisticated tokenization algorithms. I used NLTKs, word tokenizer function. I used Spacey to do tokenization. They take longer, and so I just did a brute force quick manual tokenization on one of my helper functions right there. It's just it's a find all in the regular expression module. Anyway, let's look at runs. Let's look at runs in Brown corpus. Now we have 302 occurrences of run or runs in Brown corpus. Let's take a look at some of these. So he would not run for re-election. Okay, that's running for election. Paid out would run billion or more in the first year. Medical benefits paid out would run billion or more in the first year. Okay, so run billion. Said today Jones will run well ahead of his GOP opponent. So that's another run for election type thing. He had decided to run and wanted that Mr. who lives in Queens to replace. I think that's another run for election, run for office. Let's see. Streetcar tracks run down the center of Pennsylvania. Okay, that's tracks running down a street, it looks like. There's a hit run car. Let's see, right here we have 2-run homer by this person. That's a baseball run. Okay, tied the game and single runs in the 8th and 9th. Gave the Athletics their 5th. So that's another baseball run, like how to score in American baseball, right? The winning run, another baseball run. Their runs off. Oh yeah, so that's another baseball hits and all runs. So the point is that the word run or runs is polysemous, right? Or it's a homonym with several meanings, right? You can physically run, or you can run for office, or your tracks can run down the middle of the road, or you can have runs in baseball. So let's see if we get the sentence embeddings. Let's create the sentence embeddings here. It runs pretty quickly. And we should have 302 by 384. We do. So our 302 concordances or keyword and context lines for run or runs in Brown corpus. And each of those has 384 columns or numbers. So here, let's do the k-means clustering again. Let's look at this here. And so where do we see an elbow? Well, it's not super clear. Kind of very gradual. I'm going to say 3. I'm looking right here at this number, this dot right there. That's at 3 clusters. Maybe there's a joint there, like a bend there, because this is a little bit straighter that way. So I'm going to say 3. Okay. That's what that plot does. It says, where is a good point? I'm going to say about 3. And there we have, it did the k-means clustering there. There are the labels. Let's add those to our concordance lines and double check they went through correctly. And yeah, we have the concordance lines with the file name, the offset, the word offset, and the left context node right. And then now we have the cluster column on the far right. As you can see, we have 2, 1, 2. Okay, so that's cool. Let's go take a look at, say, cluster 0. What does cluster 0 have in Brown for run or runs? We have 2-run homer. Okay, single run, that's baseball. Orioles got a run, that's baseball. Drove in runs on a freshman average, completes the bird squad. Okay, that's, yeah, high of homers and drove in runs. That's, again, baseball. 2-run double, unearned runs, and 2 victory, the Chicago White Sox. Again, this is all baseball. Baseball runs, it looks like to me. Had their last run in the 6th. Yep, 6th inning. Okay. By and large, we're looking at baseball. There might be exceptions in here, but these seem to be baseball runs. Home runs, predict runs, home runs. Yeah. Cool. Let's go look at cluster with an ID of 1. What do we see here? Okay, the reports that he had decided to run and wanted that looks like running for office. Barnes hit and run car. Let's see, the widow of the man killed last November by Barnes hit and run car. Okay, that's different. Hit and run. Pleaded no defense to manslaughter and hit and run charges were fined by the judge. Okay, that's a hit and run. The winning run, rookie, southpaw. Okay, so this is, again, baseball. So we can see that's not perfect. It's not going to cleanly separate everything perfectly, but just based on these words, it's just simply basing on the words left and right of run and runs. It's trying to put these into cohesive clusters or groups. Anyway, let's take a look at group 2. And will not run for re-election. Run. So you can see that it's not super clean, but the idea is kind of cool to take a large language model, take a sentence transformer model to create sentence embeddings. Again, I'm going to air quote sentence here because it probably are not clean sentences. It's just n number of words left and right. Again, trying to specify how many you should put, like 5 words or 10 words or 7 or something. That would might be good to do. You're probably gonna have to just do a little trial and error to figure out how many words is best. But it's kind of cool to take these numbers that come out of this sentence embedding model, which are just a bunch of round numbers. I don't have them right here right now. And then use k-means clustering to try and create cohesive clusters. And then just simply filter on those clusters so you can look at hopefully cohesive senses or meanings of the words that you're looking for. So there you have it. How can we semantically organize concordances, aka keyword and context lines, in a corpus? We can use a large language model that does sentence embeddings, and then use k-means clustering, which is a simple machine learning algorithm to do that. So not too hard. Again, I'll leave a link to this Google Colab notebook in the description of this video if you'd like to look at it. Now, it's not going to be a fully reproducible example where you can just click, 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 because I'm not going to upload the corpora. But you can look at how I used the large language model, the sentence embedding model, which I used down right in here. And if you want to see how I create the concordance lines, you can see that right in here, left and right context, and then the k-means clustering as well. So there you have it. Kind of a pretty cool way to use a large language model to create sentence embeddings that you can then use to create cohesive or somewhat cohesive concordance lines for corpus linguistic analysis. There you go. Hope you liked the video. If so, give me a thumbs up, por favor. And don't forget to subscribe and like, whatever, you know. Thanks so much. See you next time.